Testing, okay. All right, yes, thank you. My name is Nick Rossler. I'm presenting Protecting the Stack with Metadata Policies and Tagged Hardware. This is joint work with my advisor, Andre Dahan. Okay, I'll start with an overview of the research. We note that the call stack is a vulnerable system component. Lots of critical software today, such as operating systems and device drivers, are written in low-level, memory-unsafe languages like C. There are lightweight defenses for the stack, such as stack canaries. These impose only a few % overhead, and so they're widely deployed, but they're insufficient in actually protecting the stack. There are some heavyweight mechanisms, such as full software memory safety. These provide us with good security properties, but they're too slow to be used in practice. In this work, we look at creating stack protection policies for a general purpose tagged architecture. We find that we can provide object-level protection, and we can optimize our policies to only impose a 3 or 4% overhead. Our key optimizations allow us to remove the need to proactively tag and then clear stack memory, and we'll see exactly how this works and what it means later on. As an outline for the talk, I'll remind you about what the call stack is, how it works, and how it's attacked. I'll then introduce our tagged architecture, which we call the pump. We'll then see how we can use the pump to protect the stack. Then we'll look at some results, performance results, and some optimizations to make the policy run faster. And lastly, we'll summarize. Okay, so some background about the call stack. The call stack is simply a data structure for maintaining the abstraction of a function call. Each time a function is called, our program will push a new stack frame onto the top of the existing stack. The stack frame will serve a few purposes. A function will allocate space for its local variables, the return address of the function, passed arguments, spilled registers, and a few other things as well. Let's look at an example of the stack memory while a function is running. So on the left, there's a simple function f. It takes a and b. I feel like I have a lot of echo. There's a function f. It takes a and b and returns a squared plus b. Below that, there's a main function that calls f, simply passing in some arguments. Let's assume that our main function is already running. Main will have allocated space for its local variables x and y, as well as its frame pointer and its return address. When main calls f, this causes f to push a new stack frame onto the top of the stack. F will allocate space for its local variable result, as well as its return address and its frame pointer. The return address belonging to f points back into main. When f is finished running, it releases its stack frame and follows its return address, and control resumes back in main. We're now back to where we started after having called f. So to remind you about how a classic stack attack works, let's look at a simple buffer overflow. On the left, I've shown a vulnerable C function, and on the right, I've shown its corresponding stack frame. Vulnerable copies from the car star input into a local buffer of length 8. If more than 8 bytes of input are provided, the program will copy off the end of buff and onto whatever happens to be next in memory, which in this case is a frame pointer and a return address. This allows an attacker to overwrite the return address and then later hijack control flow when the program goes to use the tampered return address. Recall that all of these other things end up on the stack as well. The other local variables, spelled registers, arguments, and these can also all be overwritten to mount attacks as well. We note that an attacker will hijack instructions or pointers to access the wrong stack objects when they're doing an attack like this. And so from a security perspective, wouldn't it be useful if the stack was labeled? What if we knew something about each of the words stored in our stack memory? On the left, I've shown the vulnerable C function from before, as well as some dummy functions that simply call this function. And on the right, I've shown a stack memory. So what if we could assign a color to each one of our functions? That might look something like this. We now have a green function, a blue function, and a red function. And then what if each of our functions could color the memory that they allocated with their corresponding function colors? Our stack might look something like this. Abstractly speaking, we can see how this might be useful for coarse-grained frame-level protection policies. Perhaps now we could detect if a green buffer overflows its frame and writes into some blue memory. If our labeling was more precise, that is, we knew not only which function allocated a piece of memory, but which of the objects was stored there, we might have something like this, and we can see how this might provide the footing for more precise protection. To make use of all of these labels, what if our instructions and our pointers were labeled as well? So perhaps we could say things like, this instruction stores a blue return address, this memory word now contains a blue return address, and this instruction should load specifically a blue return address. Or this pointer is a pointer to a green array called buff. So this policy is one of the 3 policies that we look at in the paper. And the rest of the talk, I'll focus on just this policy. We'll see how we can define it more precisely, and then enforce it and accelerate it with the tagged architecture. And then we'll optimize it so it only slows our programs down by a few percent. With that, I'll take a step back and look at the tagged architecture that we're going to implement this policy on top of. Our tagged architecture is called the pump. This is short for the programmable unit for metadata processing. So a normal CPU has some amount of state shown in blue, such as registers, A, B, C, and D, a program counter that tells us where we're at in our program, and a memory. In our tagged architecture, we extend each of these pieces of state with a tag shown in green. When the CPU is running a program, such as this one, we will check each instruction against a tag-based security monitor, shown here. The inputs to the security monitor are all of the tags that are relevant for this instruction. In this case, that's the tags on the operands, A and B. We'll also take in the tag on the program counter. This instruction itself lives somewhere in memory, and so we'll take in the tag on the instruction. And then lastly, the opcode of the instruction will be an input as well. In turn, the security monitor now computes a function of 5 inputs, which are the arrows shown, to decide if the operation should be allowed or not. If it decides yes, the operation should be allowed, it must provide a tag for the result of the operation, which in this case would go on the tag on register C. In our architecture and its corresponding programming model, policies are written in software. That is, the security monitor is just a program. The hardware accelerates the security monitor by caching a subset of the recently encountered rules in a hardware cache, where a rule is just a set of the inputs and the output. In the case of a cache hit, we can then check the policy in a single cycle without slowing or stalling the CPU at all. There are optimizations that can drastically reduce the area and energy overheads associated with adding all these tags onto our chip. I'll refer you to the paper site here for more information about the optimizations and the architecture. Prior work has shown how this architecture can express and accelerate a range of security policies. These include taint tracking, control flow integrity, type safety, heap safety, information flow control, and others. The contribution of this paper is looking at how we can protect the stack with this architecture. Our stack policies end up being some of our more involved policies, and they bring up some new challenges. Okay, we'll now tie this back to looking at the stack labeling that we looked at a few slides ago. So we have this architecture. It provides us with a tag on every word of data in the system. We can write rules to describe what operations are allowed and what their results are. And we have some hardware that will remember the rules that we've encountered. On the left, I've shown a simple program. It is trying to write to a local variable x. And on the right, I've shown a stack frame. I've highlighted the instruction that's doing the store, and we can see that x is at the top of the stack on the right. So we can now communicate the intent of this instruction. That is, it should write specifically to this red x by placing a tag on the instruction. We can then write a rule that says if the instruction tag is store red x and the memory tag is red x, then this operation is allowed, and the result is that the tag should remain red x. Our software can be written more generally. We can say if the instruction tag is to store some color C containing some object identifier n, and the memory tag is colored C and contains object n, then the operation is allowed, and the result is that the tag should remain colored C containing object n. So what does a violation look like if we try to take this instruction and write to a different item on the stack, such as the return address in the frame below? Well, the instruction tag is store red x, but the memory tag is blue return address. This does not match the above rule, and we can terminate the program. Okay, so with this, we can see how we can check a stack access. What else do we need to finish building out this policy? Well, for one, we've assumed up to now that the stack was already tagged. We have to tag the stack. To do that, we add instructions into the prologue that tag the allocated frame. These instructions get a special tag setMem that allows them to claim unused memory. In general, we'll maintain this invariant that unused stack memory has a tag, a special tag, empty stack. So with this, we can tag our stack frame. We now need some rules that can describe all the valid ways that stack memory might be used. One such way is by offsetting the frame pointer to access a scalar local. We saw how this works on the last slide. Memory can also be accessed through pointers. To capture this kind of access, we tag the instructions that create pointers in such a way that the pointer produced has the correct label on it, and then there are rules that allow you to use pointers to access memory if the tag on the pointer matches the tag on the memory. A last kind of access that we see on the stack is arguments. Arguments are a special case in that they're owned by one function or one color, and they're accessed by a different color. The way that we check that arguments are accessed by the intended consumer, those details are in the paper. Lastly, we have to clean up our stack memory when we return. To do this, just like in the epilogue, we add new instructions here, and these have a special tag, clearMem, that allows us to release the frame that's owned by this function and set it back to empty stack. Okay, with this, we've seen a complete policy, and we can look at some results. So we simulate a tag processor with an in-order 5-stage pipeline. We use GEM5 for performance statistics, and we measure our overheads on the spec benchmarks. Here are the results. There's performance results. There's one bar for each benchmark showing the overhead, and the overhead is broken down into components. The average overhead for this naive implementation is about 12%. The yellow here corresponds to the miss handler. This is the software that runs whenever we take a miss in our rule cache. We can see that this is a very small contribution of the overhead. This is because the rules for this policy are very cacheable. The number of rules we need depends on the number of functions that there are, the number of colors that there are. We find that there are about 2,500 functions on average in the spec benchmarks. These are compiled with -static, so these are including all the libraries. But only about 400 are used, and only about 90 functions are active in the working sets of the benchmarks once they reach steady state. This means the rules are quite cacheable. We encounter function foo, we cache all the rules that we need for foo. The next time we see foo, we already have those rules cached, and we don't need to consult the policy software. Okay, so the largest cost we can see, shown in blue, is the instructions that we're adding to tag and then clear stack memory. For example, we can look at strang, and we can see that there's quite a large overhead just for this one source of overhead. Okay, so the largest cost we noted was tagging stack memory. The worst offender was strang. There's a large 60% overhead just for keeping its stack memory tagged. So what's going on here? Strang is a chess playing benchmark. It rapidly allocates large 16 kilobyte frames. These frames contain a buffer, and the buffer is sized for the worst case number of chess moves that we might find. But in the common case, a much smaller number is actually found. There's a lot of pruning, and so most of the memory goes unused. But our policies still have to tag these large frames in the prologue and then clear them out again in the epilogues. We find that most other benchmarks with high overheads had a similar root cause. That is, they're allocating more stack memory than they actually need. We attribute this to the fact that programmers know that on most systems, stack memory is cheap, O of 1 to allocate, and the way that programmers program they take advantage of this fact. However, we're making allocations, cost O of n. We're asymptotically changing the speed of stack allocations, and so this can cause some performance problems. So a natural question is, do we really need to proactively tag our whole stack frames in the prologue and then clear them out later in the epilogue? Instead, what if we're lazy? We look at two different kinds of laziness. One of them we call lazy tagging. With lazy tagging, we don't tag memory in the prologue. Instead, we allow the first writer to claim any memory words tagged empty stack, and they'll update the word with the tag of the writer at the time that the write occurs. In other words, we're combining the initial tagging with the first program write to that memory word. So we don't bother tagging something if we're not actually going to use it. With this optimization, we still keep the whole cleanup loop in the epilogues to maintain the invariant that unused memory remains tagged empty stack. And this allows us to remove about half the overhead. Most of the overhead came from the tagging and clearing, and we can get rid of about half of it with this optimization. It turns out that we can take laziness one step further, and we also look at lazy clearing. With lazy clearing, we also don't tag memory, we don't clear memory in the epilogues. Now, with the rules we've seen so far, this would cause problems. This means a function returns, it leaves its tagged frame still on the stack, and the next function, which goes to run, will use the same memory, and it'll try to write to that memory, but now that the tag of the last function is still there. And so with this optimization, we allow all writes to succeed. And we only check on reads that the tag that we read is the tag that we expected to read. So if all writes can succeed, what happens when a buffer overflows a return address? Well, the write's allowed to succeed. But the return address, which used to have a tag like blue return address, takes on the tag of the writer, which is something like green buff. And then later when we go to load the return address, we can tell that the tag has changed and something has gone wrong. In other words, with this optimization, we're only enforcing a data flow integrity property. When we go to read something, we can tell if those bits didn't come from the place that they were supposed to. Okay, how much benefit do we get from this laziness? I've shown the baseline in green, the performance with just lazy tagging in blue, and the combined effects of lazy tagging and lazy clearing in yellow. Together, these bring the overheads from about 12% down to only 3.6%. There's one more optimization we look at in the paper where we consider adding a new instruction to the architecture that allows it to tag or clear a whole cache line at a time instead of just one word at a time. This doesn't asymptotically change anything, but it gives you about a constant of 8x speed up. This is an alternative to the lazy policies, or it can be combined with lazy tagging. And those details and results are in the paper. Okay, to summarize, current stack protection mechanisms are either too weak, such as canaries, or too expensive, full software memory safety. And so people have looked to hardware solutions. In this work, we create stack protection policies for this general purpose tagged architecture, and we find that we can enforce object level protection. We find that lazy variations of the policies can reduce overheads down to only 3 or 4%. So tagged architectures are a good match for these data flow integrity style policies. In this talk, I only looked at one policy, which we call static authorities in the paper, but there's some other policies in the paper also, so you can check those out. And thank you for listening.
All right, questions? There we go.
A nice piece of work, certainly, and a lot of detail. So my question, though, is to ask you, as now an expert in this aspect of software security, why is this problem so hard? It is, I believe, 30 years since I woke up one morning and found that the entire internet, which was fewer than 10,000 machines at the time, had been taken down in part by stack smashing. I don't think a year has gone by that I have not heard of a new solution to this problem. All that time, 20 years after that happened, I wrote a retrospective about it, and I looked at CERT and buffer buffer overflows were the main thing, not stack. But still, it's the general principle. Why is this problem so very, very hard? Now that you've looked at it, why do we have to keep solving it?
Can you tell us who you are, and in general, please tell us your names.
I'm Hillary. Hi.
Okay. Yeah, I don't think I have anything particularly insightful. So we have a ton of legacy software that's written in these memory unsafe languages, and so there's a huge amount of software out there. I guess in general, there's checking every memory access in software adds a lot of overhead, and so solutions that are only software-based are going to be too expensive to be used. And so there's a number of different hardware ways to accelerate this, such as like hardware support for bounds checking, and that's one possibility. Our architecture can express a lot of different kinds of policies, and so we're kind of heading in that direction. But yeah, I don't think I have any magic answers for you. But.
Please find a magic answer.
I'm Dan from Google. How do you handle tagging of recursive functions? Because especially with that lazy write, it seems like the function should be able to overwrite the return address and still be counted as okay.
Mm-hmm. So in this policy, there's one function, there's one color for each function, and so if there's multiple instances of the same function in a stack, they'll have the same color, and so then you can write, if you have a pointer to a green buff, you can write to any green buff, and if there's multiple green buffs in a stack, you can write to any of those. There are other policies we look at in the paper where we do more isolation by instances, and so basically we're trying to take advantage of a cache, and so we're trying to reuse our rules, and so we're looking at trading off between security and performance, and there's a few different ways you can do that. There's another policy where we use depth instead, and this would give you protection against recursion. So there's some of the things you can do about that. But.
Cool, thank you.
Yep.
Hi, this is Salmin from Intel Labs. Sorry I haven't read your paper, but if you are thinking of hardware support for tagging full cache line, so how do you envision to protect local variables for fewer bytes, like 1 byte, 2 bytes, those kind of things?
Mm-hmm. So I guess one option is padding, and so that allows you to place a tag on a whole word and only have one thing in that word. You can also have rules, and your rules can take like a byte input, so you can see which thing you're accessing. And so if you want to have subword tags, if you want to have like 8-byte words but 4-byte tags, you could have whether you're accessing the first or the second word as another input into rule cache. And so that can allow you to support that. And then the software that runs can check to see, yeah.
Yeah, I can see there will be like much overhead, but we can talk offline.
Okay,
Yeah, thanks.
All right. We are out of time. Let's think of it again.
okay, thank you.